Hey everyone, welcome to The Explainer. Today, we're literally pulling back the curtain on the invisible engine that's running our modern lives. Every time you buy a plane ticket, check your bank balance, or register for a class, you are interacting with a massive, incredibly complex piece of technology called a database management system. Most of us never see it, but without it, our digital world would grind to an absolute halt.
Okay, let's dive into this. Here's our agenda for today. We'll start with the building blocks of data, figure out what a DBMS actually is, and then look back at the file processing problems of the 1960s. After that, we'll cover the rules, the risks, how this works in the real world, and finally, wrap up with the pros and cons.
All right, Section 1, the building blocks of data. We're going from raw facts to meaningful records. Before we can understand how to manage a massive database, we really need to know what it is we're managing. Think about the number 1, the letters ABC, or the number 19. Just floating around out there in the digital ether, they're completely meaningless, right? They're just isolated facts and figures. They have absolutely zero context. But watch what happens when we give them a little structure. If we organize those completely random facts into columns and rows, boom, instant meaning. The 1 becomes a roll number, ABC is a name, and 19 is an age. Together, this row becomes what we call a record, or a tuple. We've just transformed raw data into actual, meaningful information. So now we have this basic table, or a relation, linking a student's roll number to their address. And yeah, this single table is super useful. But the real magic of a database, it doesn't happen in isolation. It happens when we create a related collection of these tables. Let's see how this builds. Imagine a second table that links that exact same roll number to an academic year. Because both of these tables share a common attribute, the roll number, we can actually link them together. We don't have to cram every single detail about a student into one massive, unreadable spreadsheet. We can keep things clean, modular. And we can take it even further. Say we have a third table linking the academic year to a specific hostel. By linking all these tables using those common attributes, it's like a giant puzzle coming together. We can finally ask the system really complex, multi-layered questions, like taking the age from the first table, the year from the second, and the hostel from the third. We can instantly figure out which hostel does the youngest student live in. And honestly, that is the true power of relational data. Moving right along to Section 2. What is a DBMS? The brains behind the data. So we've got all these perfectly structured tables, right? But on their own, they're static. They're just sitting there. We need an active system to manage them. A database management system, or DBMS, isn't just the data itself. It's the collection of interrelated data plus a set of really powerful programs designed to access, safely store, and efficiently retrieve that information. It's basically the essential invisible rule maker keeping everything in check for a business. Picture a payroll officer, a customer service rep, and a sales manager. They all need access to company data, but they absolutely should not be seeing the same data. Payroll needs financial records. Sales needs stock levels. The DBMS sits right in the middle, like the ultimate traffic cop. It lets different users securely access their own customized views of the exact same central database at the exact same time, without interfering with each other or seeing things they aren't authorized to see. All right, Section 3, the file processing problem. Welcome to the 1960s data dark ages. To really appreciate how game-changing the DBMS is, we kind of have to look back at the absolute chaos that forced computer scientists to invent it in the first place. Before the DBMS, companies just dumped information into scattered, isolated operating system files. Finding anything was a total nightmare. Modern systems are centralized, integrated, and incredibly fast. But to grasp how bad the 60s were, let's look at a very specific scenario. Think of this as the double major dilemma. Imagine a university back in the 60s. You've got a student double majoring in music and math. Because the files are totally isolated, the music department has one file for the student and the math department has a completely separate one. One day, the student moves. They update their address with the music department, but what happens? The math department still has the old address on file. This is called data redundancy and inconsistency, and let me tell you, it was a massive, extremely expensive headache for early tech. Which brings us to Section 4, Rules, Risks, and Solutions, High-Stakes Data Disasters. Having the wrong address for a student is annoying, sure, but in the real world, data errors can be completely catastrophic. Imagine you're transferring $500 from your checking to your savings account. The system deducts the $500 from checking, and then, at that exact millisecond, the power goes out. The server crashes. When the system comes back online,
The $500 is gone from checking, but it never actually made it to savings. It just vanished, literally disappeared into digital thin air.
And that right there is exactly why a DBMS enforces incredibly strict rules like atomicity. Atomicity is a rule that says a transaction must happen in its absolute entirety or not at all, no in between. So if the system crashes mid-transfer, the DBMS realizes the job wasn't finished and automatically rolls everything back to exactly how it was before you even hit transfer. Your money is totally safe.
Now here's another wild scenario. Imagine a super popular college course capped at exactly 40 students. Currently, 39 are enrolled. Now, 2 students sitting in different dorm rooms hit the register button at the exact same fraction of a second. Without a DBMS, both of their computers check the system, see 39 students, realize there's one spot left, and tell both students they got in. Suddenly, you've got 41 students in a 40-seat class. Not good.
This concurrent access anomaly is even scarier when we're talking about banking. Imagine a department with a $10,000 balance. 2 clerks simultaneously withdraw money, say $500 and $100. They both read the current balance is $10,000. Clerk A's program subtracts $500 and writes back $9,500. Clerk B's program subtracts $100 and writes back $9,900. Whoever hits enter a millisecond later overwrites the other person's work, leaving you with completely incorrect financial records. A DBMS prevents this. It meticulously coordinates these concurrent accesses, acting like an invisible supervisor so files never collide like that.
Section 5. DBMS in the real world. Powering everyday life. We've talked a lot about the theory and the history. But the truth is, you rely on a DBMS constantly. Universities use them to track your grades. Airlines, which, fun fact, were actually some of the very first to use geographically distributed databases. They rely on them so someone in Tokyo and someone in New York don't book the exact same seat. Banking uses them for everything from your car loan to high-speed automated stock trading. And telecom companies use them to track millions of split-second phone calls and data balances.
And finally, Section 6, the pros and cons. Let's weigh the trade-offs.
As incredible as a database management system is, implementing one isn't just waving a magic wand. First, let's look at the huge wins. A DBMS acts as the ultimate supervisor that those old 1960s systems were desperately missing. It completely controls redundancy, so our double major student only updates their address once. It improves data sharing. It enforces strict integrity rules, like making sure a zip code only contains numbers. It guarantees consistency during system crashes, and it provides really deep, customized authorizations.
But we've got to be honest about the heavy costs here. A DBMS is incredibly complex software. You need highly trained developers just to manage it. And because of all that complexity, it eats up a massive amount of memory and is super expensive to run. On top of that, because it's built to handle everything generally, it can actually be slower than an application built for one specific task. But the absolute biggest vulnerability, it is highly centralized.
Which brings us to this final thought. Because all the data and the control are centralized, if the main DBMS goes down, absolutely everyone, from the payroll clerk to the customer trying to buy a plane ticket, is entirely locked out. It brings up a pretty profound question about our modern infrastructure. If a single central database failure can impact everyone globally, are we building systems that are simply too centralized to fail? Definitely something to think about the next time you tap your credit card. Thanks so much for joining me on this explainer, and keep asking the big questions.